Last class we started with our second module of system software, and we started with the absolute loaders, right? So that's what is the discussion we had in the previous class. So the loaders should actually copy the object code into the designated address. That's what is the actual task. Apart from this, few loaders do the linking as well as the resolution of external references. Yes, that's what we call it as linking. And reallocation of the object code will also be done by the relative loader, which we haven't seen. We're going to see further. Right. So we have seen the design of absolute loader, which we're going to do the absolute loading in one pass. The entire loading will happen in one pass. The reason remains to be is it's an absolute loader, wherein the address is pre-specified while writing the program itself. And after the assembly, the object code is supposed to be placed in the same address. So there won't be any reallocation happening. So for that reason, this is a very simple sort of loaders. And the absolute loaders has its significance in the bootstrap loaders, wherein the operating system or the initial routines need to be loaded into a specific locations which are fixed. So at those particular cases, we're going to go for, or we're going to opt for absolute loaders, not specifically for the user programs. But anyway, the design of the absolute loaders we have seen one program which has been assembled starting with the address 1000, and all the object code is assembled considering the 1000 address, and we have got the header record and text record and end record that is loaded onto the memory starting from the address 1000. So we have seen the algorithm of this, and we have seen one more example. We have seen the algorithm of absolute loader, wherein we start from the header record. We'll just check the text record. We're going to check the header record. We're going to check the size of the program. We'll confirm that whether the size of that program can be fit into the allocated memory, and is the designated address and the load address are both the same. If yes, yeah, we'll proceed. We're going to take each text record until we encounter the end record. We'll just copy the source program to the load address. But during this, we're going to do one more task, that is the ASCII representation will be converted into a hexadecimal character representation. Meaning in the ASCII representation, each character in your object code consumes 1 byte, but now it is going to be reduced to half byte. That's what we call it as hexadecimal character representation. Means to say actually the size of your program is actually shrunk to half of it. Right. That's how the things happen. Fine. Proceeding further, we have seen bootstrap loaders. The loaders which are started as soon as our system is started. The first loader that is actually loaded by your BIOS onto your memory is called as bootstrap loader. The task of your bootstrap loader is to load the operating system in the designated address. So bootstrap loader by default is an absolute loader. Please remember, bootstrap loader is an absolute loader. Right? How exactly this bootstrap loader works is what we're going to understand this. And here, the question may be asked something like, write an algorithm for the working of bootstrap loader. If it is asked, we have one program as an example. The same you are supposed to write considering the assumptions. The program itself is acting as an algorithm, right? And because we have to make many assumptions of the bootstrap loader, I don't know where exactly is the boot sector and where exactly it's supposed to be loaded. So for that reason, we have made some assumptions, and we're going to invoke the bootstrap loader based on that assumption. Bootstrap loader is an absolute loader which is invoked by your BIOS so as to load the operating system into the designated location. That's what is the understanding we can take. Yeah. Moving further, the bootstrap loader here we are going for the assumption. We'll go into bootstrap begins at address 0 and loads the operating system at the address 80H. This is what is the first assumption what we are taking, right? And each byte of the object code is to be taken from a device F1. Let's assume that this F1 may be our secondary storage device or hard disk, And from the hard disk, we're going to take the operating system and load it onto the address 80H, right? The object code is loaded into the consecutive location starting from 80H. That's continuously happen. The example we're going to see. But before the example, I think I have told you this, but anyway, I'll repeat this particular thing. We have made some assumptions. It's not assumptions, decimal to ASCII to hexa representation. That's all. Because we're going to be using these things in our algorithm for Bootstrap Loader or the example for your Bootstrap Loader. This should be written or means conveyed in the same way. So we cannot make our own assumptions. So that's the reason we are looking at. The decimal 48 represents ASCII character 0, which represented in hexa as 30H. Okay, and 49 to 57 decimal is representing the characters 1 through 9, because our SIC or SIC program is made up of either the digits 1 to 9 or A to F. That's the only things what we're going to see in our object. So for that reason, we are supposed to represent 1 to 9 as well as A to F. So 49 to 57 decimal is represented as character 1 through 9, and that is represented as 31 to 39H. Similarly, 58 to 63 represents A to F, that is 10 to 15, specifically speaking about the decimal values. Okay, and it is represented in hexa as 41H to 46H. And 128 is taken as 80H, which is our starting address for our loading of the operating system by the Bootstrap Loader. And the EOF, the end of the file, is represented as 04H. So now with these assumptions, we are ready for proceeding with our example or algorithm of Bootstrap Loader. Okay, we shall see that. This is our first part of our Bootstrap Loader. Here we have a function or a subroutine called as getC. Please observe this and understand. Okay, this particular Bootstrap Loader reads the object code from device F1, which we have already told, into the memory starting at the address 80H, because it is the load address which we have considered. After all the code from F1 is being entered into the memory, the Bootstrap executes a jump address to 80, because after it is been loaded, we should start execution from the 80H, which is the start address. To begin the execution, the program just loaded. Register X contains the next address to be loaded. Means that is nothing but the X will going to have the length of the next, means current object code, because that should point to the next object. That's the simple understanding what we get. Now see the algorithm or the program starts something like this. We are clearing the accumulator, means accumulator is loaded with 0. LDX hash 128. Please observe anything that is starting from hash, we are taking it in decimal. We are taking it in decimal, hash 128. You can see hash means 128 is representing the 80H. That is our starting address of the program. 80H, it is representing the starting address of the program. Right? Hash 128 means we are initializing the X register with 80H. We can assume like that way. That 80H is nothing but the start address where your operating system is supposed to be loaded. Fine? And then immediately, unconditionally, we are jumping to J sub getC. Means we are calling a subroutine getC. This getC is responsible for getting the text records from the F1 device and check that whether it is 1 to 9 or whether it is what you call A to F, or whether it is end of a file, or whether it is less than 0. If it is less than 0, it should skip. If it is anything between 1 to 9 or A to F, it should give it back to our main program, and the main program will convert it into the hexadecimal character representation and then store. So nothing is eliminated. As we learned in the absolute loader, the whatever is the character we are getting from the loader will be converted into the hexadecimal character representation, and then only it will be stored. We shall see. So we are jumping to getC function or getC subroutine. We shall see the getC subroutine. The getC subroutine to read one character from the input device, obviously, because every time whenever we read, we use RD command, we're going to be reading 8 bits or 1 byte at a time. Convert it from to ASCII to hexadecimal digit value. The converted digit value is returned in a register A, means it will be put into accumulator. When the end of file is read, the control is static. Stop means the getC function is stopped, and the control goes to ATH, which is the starting address from where we are supposed to execute. Yeah, we shall see the code of this what do you call getC function. First instruction is test device. As usual, when before reading, we're going to test the device. Test device input. And you can see at the end, the last but one statement before the end of the program, we have declared input as a hexadecimal representation or hexadecimal constant as F1. That is the hexadecimal equivalent code for your input device F1. The input device may be your hard disk or whatever. We are not concerned with that. Usually your operating system will be stored in hard disk. So F1 here represents your hard disk. So the first instruction of getC is testing the input device. And if the testing gives you greater than or less than, then the device is free. If the conditional code is set to equals, then the device is busy. So jump equal to getC. When and if it is the conditional code are set to 0, 0, we go back and test device again. This is program control IO. I think I have told you already during SIC and SIC-XC. Now we shall keep on repeating this testing until the device becomes free. Once the device becomes free, we do read device RD input. Means we read one character from the input device, that is from F1. Okay. After reading one character from the F1, that will be anyway placed into your accumulator. We are comparing the contents of accumulator with value 4, hash 4, hash 4 again decimal, hash 4 again decimal. I shall take you back. Hash 4 or 04 is indicating end of the file, right? So we are checking whether it is an end of the file. Hexa 04. Yeah, is it an end of the file? We are checking whether it is equal to end of the file. If it is end of a file, yeah, I should stop reading. We have reached the end of the operating system program. So we should jump equal to 80. Comparison, if it is giving you yes, your read character is equal to 4, then you should stop reading further and you should go back to the starting address where the execution began. That is nothing but 80. See, 80 is written in without hash because it's an address, right? And 4 is written is with a hash, which indicates that it is a value. Fine. Then we are, if it is not equal to, yeah, it is else if statement like this. Compare the contents of accumulator with hash 48. What is hash 48? Here 48, which is representing your either 0. The hash 48 is 0. That is your 30 hexa, right? Means we are checking hexa 30. That means whether the character you have read is 0. If the character is a 0, either it may be a comment or there is no instruction. Anything may be happening. So then what we're going to do, jump less than to get character. Means we just skip that particular line. If it is equal to 0, well, there is no point in loading it onto your what you call memory. So we just skip that step and we go back to the beginning of our routine getC. So one checking we made whether it is equal to 4. Then if it is equal to 4, then it is an end of a file. We just stop reading further and we go to the beginning of the execution. Second condition we check whether it is equal to or compare it with 48. If it is 0 or less than 0, means that is 30H, then it is an empty line. So skip that line. These two conditions we check. Okay, after the jump less than to getC. If it is not 0, if it is not end of the file, then it should be, it should be anything between 1 to 9 or anything between 8 to 11. Agreed? It should be, if it is not 0, it is not end of the file, then it should be anything between 1 to 9 or it is anything between A to F. That means hexadecimal 10 to 50. Then what we are doing, subtract hash 48. Again, the 0 value, that is hexa 30 from your accumulator. So you subtracted the value. and compare it with the value 10. If it is less than 10, then obviously it is something between 1 to 9. Getting the idea? If it is less than 10, if it is less than 10, it is something between 1 to 9. Am I correct? So we subtracted hash 48 from the value, whatever is there in the accumulator, and we compared it with 10. If it is less than, then the value what we have read is 1 to 9. Please understand, it is 1 to 9. Your object program is either made up of 1 to 9 or A to F. No other things can be there in your object code because it is not your assembly language program, but it is an object code. It will contain hexadecimal values 1 to 9 or A to F. So we subtracted hash 48, that is your 0 or 30H, and then we compared it with what we call 10. If it is less than 10, see the next instruction, JLT, less than 10, then return. Return to whom? Return to the caller. Who is the caller? Our Bootstrap Loader program, main program is the caller, which has called the getC. We are in now in the subroutine getC. Okay, no, if it is not less than, then again we are subtracting another sum. So as to get the values from A to F. Means it is not less than 10, it is equal to 10 or it is greater than 10. Then either that character is an A or B or so on till F. So for that reason we are subtracting 7. Right? And subtracting 7 and return subroutine. We are going to return that particular value to the main program. So your getC checks two conditions. One, whether the end of the file is reached, that is by comparing it with hash 04, or whether it is the line is not containing any value, means it is equal to or less than 30H, then it is an empty line and we skip. If it is end of the file, we'll go to 80. If it is not that, we'll skip. The third thing what we'll check is we're going to subtract the value hash 48, that is nothing but the 0, 30H from the value whatever we have read, and the residual or the difference what we have got is less than value 10. Then we have read a value either 1 to 9. Conversion of that will going to happen in the main program. And if not, we should check whether it is anything between A to F. So it should be between A to F. So then we're going to subtract another 7 and get the value between A to F. So that's what is your getC is doing. We shall go back and see our main program. See, during the loop, means at the label loop, we have called gem subroutine getC. After that, we are going to get a value. That get a value, we are doing RMO. RMO instruction we haven't seen. RMO instruction will going to move the contents of a register to the other register. So we are register to register transfer. We haven't seen register to register transfer. During register to register operation, we have seen the arithmetic and logical operation. Transfer operations we have seen. The RMO is called as register move operation, wherein contents, see, whatever the contents we have received, we have got it in accumulator, correct? And that accumulator content is now moved on to S register. Okay. After that, we are shift L is another instruction which we are using, which we call it as a shift left. Shift left, what? Contents of S register. You can see that it's not accumulator content, it's S register contents. By how many bits? By 4 bits. What we are trying to do is we are converting the character which we have read from the F1 device, which was placed into accumulator, is now transferred to S. That we are shrinking it. We are converting into hexadecimal character representation. Earlier in the Bootstrap load, means earlier in the absolute loader I told, whenever the character is read, it will be converted into a hexadecimal character representation, which means each character which used to consume 8 bits or 1 byte is now converted into half bytes. That's what we are doing by putting the value into the S register, and that is shifted left by 4 bits. That is going to reduce the contents of what you call your character that is read. And then after, means now whatever you have read is now placed in your S register in a shrinked way, right? Now 8 bits is reduced to 4 bits. The contents is in S register. Again, I am calling jump get subroutine. So which will going to get another character, because one character reduced to 4 bits, I need to get another character that also should be reduced to 4 bits. Then only we can put it into the what you call load address, right? So then what we will going to do, again I called getC. getC will going to give a character. That character is added with the accumulate, means that character which is added with the contents of X register. Getting the idea? That character is also added with the X register, means with S register. Again, when you have called getC, will return to the place where, again to the place of RMO, correct? No, register move operation. So other character is also reduced unto hexadecimal character representation, and then it will going to be stored HTCH. You can see that HTCH 0, X will going to be storing it into the address specified by X, and this goes on. And what we are doing in this TIXR, we are incrementing the X register content by 1, and then again comparing it with X register only, right? So means to say we're going to be going to the next consecutive location starting from ATH. You can see that LDX #28 is loading the 80 hexa, which is the starting address of your place where the operating system is supposed to be loaded, and we are comparing it with it, and just we are going to the next iteration of the loop. So like this way, we'll be reading a character by character, converting it into the hexadecimal character representation, and keep on storing it onto our memory location, starting the consecutive memory location starting from ATH. I think things are a bit confusing. Yes, you don't need to write these comments and all whenever you are writing about Bootstrap Loader. If at all Bootstrap Loader is asked, it is asked about the algorithm or the program for Bootstrap loading. So either of it is the same content. So you don't need to write all these comment lines on these comment lines following your instructions. Hardly you have 8 to 10 instructions here and 8 to 10 instructions here. This both together will going to explain you. Means will give us the algorithm for Bootstrap loaders. One of the usual questions. Either the absolute loader algorithm, and in loaders and linkers, there is no conceptual thing that you need to understand and solve some problem. That sort of thing is not there. Majority we have many algorithms and the working explanation. That's what is the thing what we have. No problem solving thing, just like as we had with assemblers, we don't have. And few of you have. I got a request that question paper problems being posted and been asked to be solved. Yes, we have did the SIC XA assembly, particularly in machine dependent assembler features. I have assembled the SIC XA program step by step for each instruction. I think if you go through that video, you're going to get a clear idea of solving the problems which is being asked in the what you call question paper questions. And that is sure. Either the algorithm I have told, either the algorithm of assemblers, or you will be given a code to convert it into the object code that will be asked. But when it comes to the loaders, we have the concept and we have the algorithms. Majority of that will going to be in a similar fashion. So means to say problem analytical is numerical things will be less in this case. So this about the Bootstrap loader. Please go through once again with the code and the comments so that you can understand the working better. Fine. So we are calling a function getC. The getC is responsible to read a character. Before that, it compares whether it is an end of a file or whether it is what you call a blank line. If not, it is going to read, and whether it is going to decide whether it is a value read between 1 to 9 or whether it is a value read between A to F. Based on that, it is going to return it to the main program. The main program puts it into the S register, left shift by 4 bits, so as to convert it into the hexadecimal character representation. After which it will read the next character. Again, it does the same thing and adds both of it and then loads it, stores it into the address specified by X. That is nothing but our load address 80H. So this process is repeated again and again until your getC encounters the end of a file. That is your 04 hexa. Fine. This happens again and again. Please pay attention. This it looks like only 3 slides, but the concept is a bit complicated. So you should go through one more iteration so that you can understand the concepts in a better way. Fine. Yeah. Okay. So a simplified approach is being used for that algorithm, and I don't think so. This way of writing algorithm will fetch you the marks because we all are accustomed to the way it is seen in the textbook. This is what you call verbal conversion of that particular algorithm, so that this can give you an understanding. But when you are writing the examination, you're supposed to use the earlier version which I've shown you. So this gives you just an idea, means a hint of how to remember that. Okay, X is loaded with 80 hexa. That means your load address, and we are starting with our loop. You might have seen the loop. Get C, we're going to get one character, and that will be placed into your accumulator. And means get C will going to get a character and convert it into the ASCII representation. Okay, and again a get C is called, right? Yeah, and once a second get C is called, combine the value returned from A plus S and store it in the accumulator, and then store that value into address specified by X register. Then X is incremented by 1. So after reading 2 bytes, we shrink it to 1 byte, and that will be stored into your consecutive address in specified by your X register, that is your 80H. Yeah, what getC is doing, these are the steps that it is doing. First, your getC reads a character, and then it is going to compare with 04, which is end of the file, or else it compares with 48, so as to know whether it is a blank line. If it is a blank line, it is going to just skip it. And then A minus 48 is done so as to understand whether it is the character that is 1 to 9. If not, it is not 1 to 9. Then again, we're going to do A minus 7 so as to get that whether the value, any value between 1 to, A to F. So this is a verbal representation of the algorithm for your Bootstrap loader. So you can understand it either from the program or from this. Okay. The more number of decimal and hexadecimal values leads to a bit of confusion. That's what is happening. Otherwise, it is a simple program. Fine. So one of the sure question in your examination, you may have from absolute loaders or you may have from Bootstrap loaders, as like the algorithm or explain the Bootstrap loaders working of this particular thing. But in the textbook, this contents is written in many pages. It's almost even the assembler contents is many pages, but the actual fact, what is needed exactly is been picturized in your slides. If you go through the slides, the contents of the slides is enough for your preparation. That's what I mean to say. Okay, moving further. Yeah. Next is machine dependent loader features. So we just understood the concept of absolute loader as well as Bootstrap loader. Where is reallocation loader? Yes, reallocation is a concept. For that reason, means the relative loading is also is linked with your, is associated with your linkers. So for that reason, we're going to take it up next as a feature, as a separate concept. Okay, loader means it should be an absolute loader. That is your Bootstrap loader, and your absolute loader does it. So fine. We'll take one concept next. I think already 30 minutes done. Fine. Next is reallocation. Yeah, we know that reallocation, when the program is assembled using the relative address in the format 4 instructions, for all the format 4 instructions, the address need to be added. Not only format 4 instruction, I'm talking about operands need to be added with the load address. So how to do that? We have 2 methods. One is by using modification records, which I have told you in our assemblers when we did. The other method, which we call it as reallocation bit mask. We shall see both of them, and which one should be used, what's the difference, we shall see that. So 2 methods are used to specify the program reallocation. First one, using modification bit, which we have already seen and already know this, but we are repeating that. M record or the modification record specify the start address that has to be modified according to the load address. This usually used for format 4 instructions, and that too only for operands. By default, every instruction, when it is loaded, suppose you have assembled a program starting with the address 0000, but you have allocated, This operating system has allocated the address 3500. When the first instruction is being loaded, it will be loaded onto 3500. Obviously, the next instruction will be loaded onto 3503. And it goes on. Means by default, during the loading itself, the load address will be added to your relative address. Means all the location counter values. But for the operands, this will not happen. But for the operands, if it is a format 3 instruction, either PC relative or base relative, this addition no need to be made because your PC relative or base relative will contain only the displacement. The displacement remains the same. Whether it is loaded on 3500 or whether it is loaded on 8000, no issues. Your displacement remains. If it is minus 20, it will minus 20 only. If it is loaded 3500, it will be minus 20. Fine. Or any other address, it will be that one. Displacement will not have a problem. So the problem arises only with the format 4 instruction. I think I have repeated this in your earlier classes with the reallocation also. So for those operands which is format 4 and which is having direct addressing, we are supposed to specify the modification bit or modification record specifying the starting address of the operand as well as how many half bytes from there need to be modified. So for example, we use a modification record, something like M00007 is the address from which has to be modified. How many bytes? 5 half bytes, 5 into 4. The half bytes is 4, 5 into 4. That means 20 bits from there is supposed to be modified. What modification you'll do? You will add the address copy. The copy may be the starting address or the copy may be the load address of your program that should be added. So this is what is a modification record. Yeah. The start address has to be added to the lower order 5 half bytes. It is 20 bits starting from 007. That's what it means. So we need to write one modification record for each format 4 instruction which is having direct address. So this method is inefficient and you need to the majority of operands has to be modified. So is this? But if the case is SIC version of a program, we shall discuss this. The second way of reallocation, the next class. I'll stop here. Please do go through the Bootstrap Loader algorithm again and have a practice on that because there is a lot of ASCII, hexa, and character representation, all these things. So that is going to be the topic we discussed today. So next class we shall continue with this machine dependent loader features and we're going to discuss importantly the loading link, means linking loader. That's a very important concept. Majority of the times it will be asked. Fine. Thank you for joining.